everybody, and welcome to our next video in Unit 4, which is all about neutralization reactions. So in the previous video, we talked all about precipitation reactions. So we're specifically focusing on reactions that occur in solution. So just to recall, a precipitation reaction is when you have two aqueous solutions and they come together and they form an insoluble precipitate, right? And that's why we call it a precipitation reaction. We're producing a solid from something that wasn't there previously. A second type of solution reaction that we commonly encounter in chemistry is called a neutralization reaction. And we started to talk a little bit about neutralization reactions in a previous video. But just to reiterate that, this is going back to page 2 in the notes. Neutralization reactions involve a transfer of a proton between two species in the reactant side. So we have to remember that a proton, or we could just make a note right here. So we have a transfer of a proton, but we have to remember that a proton is actually just a hydrogen ion, right? Because that hydrogen ion only has one proton. So anytime we mention a proton, that's always just a hydrogen ion. But I'm transferring a proton from one species to another species. And generally, this is done via an acid-base reaction. And that's because acids tend to have very high concentration of protons, and bases can accept those protons. So that's what we're going to focus on in this particular video. I just went ahead and I came up with this just kind of like a organizational chart that just kind of differentiates between acids and bases. So acids, which like we said, tend to contain protons. So these, we'll say donate protons, whereas bases will accept the protons. Acids tend to taste sour. So whenever you have sour candy, like Sour Patch Kids, you're consuming a whole bunch of citric acid. That citric acid is allowing your tongue to gain a whole bunch of protons when you consume it. And when you consume that, that's why you get that sour feeling, is because you're feeling, all of those protons that are transferring to your tongue. So anytime something tastes sour, it tends to contain a lot of protons in it. Acids are also very corrosive, as we know. And you might remember back in Chem 2, we did a couple of labs where we use litmus paper to test whether something had a high or a low pH. Acids tend to turn litmus paper red. You might remember the opposite, actually. So in this case, bases tend to turn litmus paper blue. Bases are also corrosive. So a lot of times people just assume, oh, it's an acid, it's bad, right? Anything that's anti-acid is good. Not necessarily, because bleach is considered a base, and bleach is not good for us as well. Bleach can be corrosive. Lye is super corrosive. They actually use lye as a precursor for soap. And I have a lesson that I'd like to teach you guys all about how to make soap, because it's a really interesting process. You take something like super corrosive, you react it with some triglycerides, basically animal fat is what they used to use back in the day, and you get soap, which we use to clean ourselves every day. And bases also tend to taste bitter as well. So I can't think of something I guess chocolate, right? Dark chocolate could taste bitter. And that's because it tends to have a little bit of a higher pH. Bases, I don't think it's on here actually, but bases have a higher pH. And we say higher pH is above 7. So we'll say greater than 7. Whereas acids tend to have a lower pH. So less than 7. And here's some examples. So I have acetic acid, I have hydrochloric acid. Acetic acid is just a fancy way to say vinegar. And some examples of bases, we have ammonia and sodium hydroxide, which sodium hydroxide is Li. And here is a dissociation reaction right here. So this particular process is showing the dissociation of an acid. So dissociation of an acid. So this right here is nitric acid. Nitric acid is going to dissociate. So when it comes into contact with water, this proton is going to isolate itself out. So I have one proton and I have a nitrate group. This right here is why nitric acid is an acid. I have a high concentration of protons right there. I'm producing protons when this dissociates. So because I'm producing those protons, nitric acid is an acid. The extent to how much or how many protons comes out of that dissociation determines the strength of the acid, which we'll get into in a little bit. Here's the dissociation of a base. So a dissociation of a base. So here's sodium hydroxide dissociating into its ions. So I have my sodium ion, and I also have the hydroxide ion. Notice here I have no proton, right? However, protons would be attracted to one of these species when it dissociates. Which species would it be attracted to? Be attracted to the hydroxide, because guess what? Protons, H plus a hydroxide gives us water. So that's why our bases tend to accept those protons, is because they produce hydroxide ions in solution. And those hydroxide ions then form readily water with the protons from acids. So here's why your acids and bases tend to form water, right? Which we talked about on page 2 as well. So protons from acids react with the hydroxides from bases to form water. And let's go back to this acid part here for a second. So, and this is not just the acid-base unit. So don't get panicked that I'm talking a lot about acids and bases right now, because you don't have to know all too much about them in this unit, just the very basics. But generally speaking, we'll go more into this in unit 8 is what I was trying to say, which we go just strictly acids and bases. So a lot of times you might see, instead of just this guy right here, you might see protons commonly written as this right here. So it's basically a water with an extra proton attached to it. And we call this the hydronium ion. Hydronium ion. Hydro, let me spell this a little bit better. Hydro, and then nium, N-I-U-M, hydronium ion. The reason why we use the hydronium ion instead of protons is because singular protons don't technically exist, because every solution that you would do an acid-base solution in has water in it. And therefore, those protons would immediately attach themselves to water rather than being separate. On paper, you might see it written this way, and that's fine. There's nothing wrong with that. But in case you do see the hydronium ion, this and this tend to be interchangeable, just so you know. Unfortunately, and you hear me say a lot of times, oh, you don't have to memorize in chemistry, and that's true, but sometimes we do have to memorize some things. And one of those things is your list of strong acids and strong bases. So your strong acids consist of, there's 6 of them. There's hydrochloric acid, hydrobromic acid, hydroiodic acid, so that's the HI, nitric acid, sulfuric acid, and chloric acid. I don't remember the name of HClO4, but it is a strong acid. And you have 6 strong bases as well. So we have potassium hydroxide, lithium hydroxide, sodium hydroxide, calcium hydroxide, strontium hydroxide, and barium hydroxide. You might notice that, especially with the strong bases, we could see some general periodic trends here. So I have lots of group 1 metals. So lithium, sodium, and potassium are all on top of one another on the periodic table in the same group. And I also have a lot of group 2 elements here as well, some alkaline earth metals. So calcium, barium, and strontium are on top of one another on the periodic table. What makes something a strong acid? Well, strong acids will completely dissociate in water. Completely dissociate in water, making them strong electrolytes. And strong bases also completely dissociate. So back what I said up here, right? The degree to which something dissociates tells us the strength of that acid or base. So nitric acid is considered a strong acid because it produces as many protons as it can in solution. It dissociates to the max. Whereas if I have a weak acid like acetic acid is not considered one of our 6 strong ones. It does not produce the maximum number of protons. You're going to have some that are left undissociated. They're going to remain together in solution. And the same goes for your bases as well. So your strong bases will completely dissociate into whatever the cation is and the hydroxide ion, whereas weak bases do not. Anything that's not considered strong is considered weak. So if I were to tell you ascorbic acid, which is vitamin C, ascorbic acid is not one of the strong acids, therefore it is a weak acid. Aniline is a base, right? It's not one of the strong bases, therefore we would consider it weak. Let's go ahead and dive into Bronsted-Lowry acids and bases. So when we look back at this, right, you might be like, wow, that's kind of got a lot of different definitions for acids and bases that are happening, right? You say, okay, acids donate protons. Okay, they make protons in the solution. Okay, they do this, they do that. In chemistry, there are so many different ways to define an acid or a base, and each way has its own practical application. And we don't have to learn all 3. I think there's 3 or 4 of them. We just like to focus on the Bronsted-Lowry definition of acids and bases, which is practically what we were talking about already. So a Bronsted-Lowry acid, right, tends to donate protons in solution, which is what we were already saying. So these tend to donate protons in acid-base reactions, which are also known as protons, remember. Whereas our bases tend to accept those protons. So acids donate the protons, bases accept the protons. However, we could also categorize the products of that reaction. So every acid-base reaction, of course, or every neutralization reaction will have an acid and a base on the reactant side of that. However, we can categorize the products of that reaction as well. And when I have an acid and a base reacting together via a neutralization reaction, I will always have 2 products. And those 2 products are a conjugate acid and a conjugate base. So what do those mean? The conjugate acid is the species that has accepted the proton. This is found in the products. So our conjugate acid is the species that accepted the proton, whereas the conjugate base would be whatever's left over after the proton has been donated, right? So the conjugate base is the species that remains after the proton has been transferred. I think it's easier to look at a equation and to see this than it is to talk more so about it. So let's just dive into sample problem 4. So sample problem 4 says, label the Bronsted-Lowry acids and bases in each of the following reactions. So there's 2 of them here. I want to identify on my reactant side which is the acid and which is the base. But in order to do that, we have to consider what's on the left side of the equation as well. Sometimes you'll have to predict, which that's a whole other can of worms. We're not going to get into that yet. But it looks like here I have NH3, and on this side of the equation, it looks like that NH3 accepted the proton, right? Because it has an extra proton right here. Whereas water actually lost a proton in this reaction. So water is going to be the acid. And that's because the acid donated the proton. This donated a proton to ammonia to produce the ammonium ion. And I now form the hydroxide ion. So water is the acid, and therefore ammonia is the base. Okay, that base is accepting that proton. That nitrogen has a lone pair on it, and that lone pair can accept a proton. So what are the products of this reaction? When I have a base that accepts a proton, right? Things that have protons tend to be very acidic. So whenever the base accepts the proton, we call that the conjugate acid. So this is the conjugate acid. And that's because NH3 gets more acidic when I add that proton, right? Because that's what makes something acidic, is it tends to have a lot of protons, or it's able to donate protons. That ammonium ion can donate a proton back to something else if it really wanted to. So we call that the conjugate acid, whereas this hydroxide is the conjugate base. And that's because if water is acting as the acid, in this case, because it's donating a proton, whatever's left over after that donation is now a little bit more basic. And I could see that because hydroxide really is what makes something a base, right? One definition is that it accepts protons, which this would to make water. But another definition is, I think it's the Lewis definition, says that anything that has a hydroxide group is going to be basic, okay? So this is our conjugate base right there. Let's take a look at this one. So in this case, water, I look on this side here, looks like it accepts a proton. In this example, I'm going from water to the hydronium ion. Remember, that's the name of that guy. And I have hydrochloric acid, and looks like hydrochloric acid is losing that proton to become the chloride ion. So in this case, my acid is the hydrochloric, because this is donating a proton to water, which makes water the base. It's accepting another proton. The thing that's left over after this is gone is what we call the conjugate base. Conjugate base. Whereas this right here, whatever has accepted the proton, is now the conjugate acid. So notice how you have to have one of each. I have to have an acid, I have to have a base, I have to have a conjugate base, and I have to have a conjugate acid. You have to have all 4 of those in a neutralization reaction in order to have one. You might be like, wait a minute, Mrs. Snyder, how the heck does water act as an acid in one case and act as a base in another case, right? And that's always a cool thing, because there are some species, especially water, that is what we call amphoteric. So I'm going to type this out because this is a little bit longer of a definition. But amphoteric means that it could act either as an acid or a base, depending on its conditions, on the conditions that it's in. So this is a chemical species that has the ability to act as an acid or base, depending on the reaction conditions. Water is one of those things that does it very, very nicely. And that's why water has a relatively neutral pH. Is it because it can act as an acid? It can act as a base. It's not very acidic. It's not very basic. Kind of just is a little bit of both in a sense. It's going to act depending on what else is there in that particular reaction. So with an acid, it acts basic. With a base, it's going to act acidic. And we call that amphoteric. Let's take a look at this next one right here. So label the Bronsted-Lowry acids and bases in each of the following reactions. Then write the conjugate acid. Then write the conjugate acid and the conjugate base for each and label. So let's get the pen back over here. Looks like I have some sulfuric acid and I have the hydroxide ion. So this one is pretty self-explanatory to see where the proton's going to go, right? I have sulfuric acid, which has a lot of protons that are attached to it. So this is our acid. In fact, this is a strong acid. And I have my hydroxide ion. So this is the base right here. We said acids tend to donate protons. So one of these protons is going to get transferred to the hydroxide. So I'm just going to draw one transfer. So I'm going to draw just HSO4, just getting rid of one of those. And if I get rid of one positively charged proton, this leftover group would have a -1 charge because here it's neutral. If I get rid of a positive thing, it becomes a little bit negative. And that positively charged proton is going to get transferred to this hydroxide ion. So if I have H plus 1 and OH minus 1, I'm left with just water. And water is a liquid. Notice how the charges also balance out. So on my reactant side, I have an overall charge of -1. On my product side, I also have an overall charge of -1. Let's identify the conjugates in this case. So sulfuric acid was our acid. And whatever's left over is going to be considered the conjugate base. I'll just put CONJ, conjugate base. Whereas this base that has accepted that proton is now our conjugate acid. Conjugate acid. And we tend to call that a conjugate acid-base pair, right? So our conjugate acid-base pair would be these two. And here's our second pair, like that, base and a conjugate acid. Let's take a look at this one right here. Takes a little bit of wisdom, and of course, like I said, chemistry takes practice. You're not going to get good at this right off the bat, but having a little bit of wisdom, right? This right here is going to act as our acid. Ammonia tends to act as a base, and that's because we have a lone pair on that nitrogen. Then nitrogen can easily accept a proton. So here, this is our acid, and ammonia is our base. So let's draw that transfer of electrons, so let's draw that proton transfer. If this particular proton, this is the one that we're going to move. Usually it's the one in the front. Same thing right here. That one in the front moved. Here, that one in the front moved. For water, one of the ones in the front moved. One way to tell if you have an acid is that it's protons in the front, which is why this one, you don't tend to show them in the front there. So getting rid of that, looks like I have acetate left. So C2H3O2 minus 1, because I'm getting rid of that positively charged proton. And then I have this ammonia that gained a proton. It's got a neutral charge. Now it's +1. Notice how I'm not forming water here. And that's okay. So that's why there's so many different definitions for acids and bases. One definition says that acid-base reactions tend to form water. That's not always true, because as we see here, I still have an acid-base reaction occurring because I'm still showing that transfer of that proton. However, I'm not producing water in this example, but still an acid-base reaction. What we can also do is to determine what side of the reaction is most likely going to be favored based on the strength of those acids and bases. So if I look here, here's the table that shows relative strength of acids and bases. So at the top, you have some of your strongest acids, right? So here's some of the strongest ones that we've talked about already. Here's your 6. So I have nitric, chloric, right there. And after that, we tend to get into our little bit of weaker acids, right? So here's phosphoric acid, here's hydrofluoric acid, which is not a strong acid, acetic acid, I have peroxide, water, which is not a very strong acid, as we know, because it also acts as a base. But our strongest acids to our weakest acids, notice that if I have a very weak acid, its conjugate base is very strong, right? So this hydroxide group, that's sodium hydroxide, calcium hydroxide. Hydroxide is the strongest base. So the stronger the acid, even if I look at the top, so the stronger the acid, when this loses that proton, its conjugate base is very weak, okay? And that's because this tends to donate its proton very easily. But if this donates its proton very easily and it forms this ion, this is not going to accept that proton very easily. So this is a strong acid because it donates that proton very well, but it's a weak base because it does not accept that proton very well because it just donated it, right? So that makes sense. The stronger the acid, the weaker its conjugate base. Or you could say the weaker the base, the stronger the conjugate acid. They're always going to be opposite. And you could use this to see really what side, which reaction would be favored over another one, or which side of the reaction is favored. And this is getting into something we'll talk about in the equilibrium unit, but let's take a look at it for this one right here. So I have this top one. I have sulfuric acid and I have the hydroxide ion. So sulfuric acid is all the way up here, right? Sulfuric acid is a very strong acid, and hydroxide is a very strong base, right? So this particular reaction happens very readily. That sulfuric acid is giving that proton to hydroxide, done, right? This side of the reaction, let's get a highlighter. Because this reaction happens so readily, we're going to have a lot of that ion, I don't know what that ion is called off the top of my head, and water in that solution. And that's because this happens very, very fast, right? It also happens very readily, I should say, not necessarily fast, but we'll say very readily. Let's compare it to this one right here. So I have acetic acid and ammonia. So here's acetic acid, somewhere in the middle, right? And I have ammonia right here. Ammonia is a relatively strong base, and its conjugate acid is going to be relatively weak, right? So because it's a strong base, its conjugate acid is pretty weak. So if I look here, this one and this one tend to exist in about the same concentration, right? Because acetic acid's like, yeah, I'll give a proton up. Not necessarily. If I feel like it, I'll give one to you, right? Because it doesn't totally dissociate. But in this case, my conjugate acid, I didn't even label these. My conjugate acid tends to be weaker in this sense. So this ammonia could basically rip those protons away from that acetic acid and again produces a lot of this right here. The reaction, the side of the reaction that's tend to be favored is the side that has the weaker conjugate acids or conjugate bases. Okay. Sometimes you might see that the reactant side is favored. I think one of these ones maybe. Nope, none of those are favored over there. I lied. But you might see one like that. Reactions don't like to have hydroxides present in solution because those hydroxides are going to take a proton from anything that's around it, right? But water tends to be very present in solution because it doesn't really react with anything, right? It's not going to take a proton. It's not going to accept a proton as easily. So just something to consider. We're going to work a lot more with this in Unit 8, like I said, which is strictly acids and bases. But I wanted to introduce it here a little bit because you might see it in this particular unit a couple times. Anyway, that's going to wrap up this acid-base section. We're going to do some more practice with this in class. As always, if you have any questions, please do not hesitate to get in touch with me, ask me those questions, and I will see you in the next video all about an even more fun type of reaction, which is the redox reaction. I will see you then. Bye.